Okay, in this lecture, we're going to continue with our Chapter 3 review material. And in this section, 3.2, we're going to talk about the graphs of functions. So in 3.1, we reviewed the concept of a function. It's some rule that assigns unique values to each point x in a set called the domain. Now, if we're talking about the graph of a function, f, the graph is defined to be the set of all points xy in the xy plane such that the y-coordinate of our point is given by the value of the function f at that x-coordinate, where x lies within the domain of our function. So geometrically, we're looking at a collection of points in the xy plane. And the graph of a function is usually some curve, which we would say is the curve y equals f of x. And for any point on our curve, we're looking at a point xy where the y-coordinate of our point is defined as the value of f at x. So intuitively, we can think about finding the graph of a function by choosing a set of x values in the domain of our function and evaluating the function f of x at those values. So here, and then the f of x value gives us our y-coordinate. That is how far we're moving upward or downward from the indicated x value. So if f of x is negative, we're moving downward from the value of x to get our negative y-coordinate. And if we choose another value of x, and we substitute into our function, and we have a positive f of x value, we would move upward from that x value to get a positive y-coordinate. So the collection of all such points in the xy plane, which are defined in this way, is called the graph of our function. So some simple functions that we'll work with, or functions whose graphs are simple, would be linear functions. So any function whose graph is a straight line is called a linear function. And in general, any linear function can be expressed in the form f of x is ax plus b, where a and b are some constants. So let's look at an example of this. In this first problem, we are asked to sketch the graph of f of x is 2x minus 3. So an easy way to sketch the graph of functions is to determine points which lie on the graph of those functions by evaluating the function at different x values. So let's consider evaluating this function at x equals 0. So when x is 0, our y value for f of x would be negative 3. So from x equals 0, we're moving downward 3 units. Now if x is equal to 1, the value of our function f of 1 would be negative 1. So our curve is passing through 1, negative 1. Then when x is equal to 2, we would have f of 2 is 1. When x is equal to 3, we would have a y value of 3. And if x were, say, negative 1, if we start moving in the opposite direction, we would have a y value of negative 5. And we start to see our line. So here, connecting our points, we see that our graph is this straight line passing through the indicated points. In general, we can recall that the graph of a linear function of the form ax plus b specifically is the line whose slope is a and has a y-intercept of b. So in the example we just considered, a was 2, so the slope of our line is positive 2, and our y-intercept was -3 here. All right. Now, in the next couple of examples, we'll look at graphs of functions which are piecewise defined, but each piece of our function is defined as a linear function. So these sorts of functions, whose graphs consist of line segments, are called piecewise linear, or piecewise linear functions. So let's look at some examples. In this next example, we are asked to sketch the graph of the function f of x, which is defined as x plus 2 if x is less than 0, and 2 minus x if x is greater than or equal to 0. So let's start with the positive values for our function here. So if x is greater than or equal to 0, let's sketch our graph. So when x is equal to 0, the y values of our function are 2 minus x. So 2 minus 0 would give me 2 here. Now when we move to x equals 1, we would have 2 minus 1, which is 1. So line passes through 1, 1. And we see that in general, we're describing here a line whose y-intercept is positive 2 and whose slope is -1. If we were to keep substituting values of x into our function, we find the indicated points in the xy plane. So for the part of our graph where x is greater than or equal to 0, we have the following line segment, whose y-intercept is positive 2 and has a slope of -1. Now, for the values of our function where x is negative, the function is defined as x plus 2. So that would be a line of slope 1 and y-intercept 2. And we can determine what this line looks like by plotting some sample points. So for x less than 0, let's say if x is -1, our y value would be +1. If x is -2, our y value is 0, and by plugging in other values of x, we find these corresponding points on our graph. Or alternatively, if we know the slope of our line is 1, we can obtain these points by moving 1 unit to the left, 1 unit downward from point to point. And we get the following sketch for the graph of our function. All right. Now in our next example, we are asked to sketch the graph of the function f of x, which is 4 minus 2x if x is less than 1, and it is x minus 2 if x is greater than or equal to 1. So here, the value of our function changes definition when x is equal to 1. We can see we've got different definitions depending on what side of 1 we lie on. So let's start by looking at the values of our function where x is greater than or equal to 1, starting at x equals 1 itself. So when x equals 1, the value of our function would be x minus 2. So 1 minus 2 gives us a -1. And then looking at the form for the equation of this line, we have x minus 2. So that would be a line with y-intercept -2 and slope 1. So we can obtain the graph of that part of the function where x is greater than or equal to 1. So here we start that definition only when x is 1. As soon as we move to the left of x equals 1, our function changes definition. So let's see how it would be defined for x less than 1. So if x is less than 1, our function is defined as 4 minus 2 times x. let's try some test values of x. For instance, if x were 0, we find y would be positive 4. And in general, this equation of our line, 4 minus 2x, is a line with slope negative 2 and y-intercept positive 4. So we could plug in some other values. Let's see what we would have when x is negative 1. If x is negative 1, we would have f of negative 1 is positive 6. And so we're looking at the line which would be passing through those points, and we'll keep extending infinitely in both directions. For both of these examples, we could keep moving for larger and smaller values of x. Now here, one thing to keep in mind is that our values of x don't need to be integers. So for this first definition, if we're looking at values of x that are greater than 0 but less than 1, we need to keep extending our line. So as the values of x are getting closer to 1, we see that the value of our function is approaching 2. So if we're getting very close to 1, the values of our function 4 minus 2x are getting close to the value 2. So our line extends, but when we hit x equals 1, the definition changes. So to indicate that graphically, we would put an open circle as the end point of our graph here, and a closed circle or a closed point when x is equal to 1 to indicate that it has a value of negative 1 there. So recall that open point or closed point notation to indicate at a point where we may have a jump in our graph, how the function is defined at that point where our jump occurs. So let's look at some examples maybe involving the graph of a piecewise function or a piecewise function in, say, economics or business. So for this next example, we are told the Birmingham Waterworks charges its residential customers a basic service charge of approximately $25 per month. Now, the first 1,500 cubic feet, or CCF for 100 cubic feet of water, cost about $2 per 100 cubic foot. And to encourage water conservation, excessive water usage is charged at a higher rate. So we're told here it costs about $4 per 100 cubic foot for each 100 cubic foot above 15. So using this information, we're going to try to build up a function for the water bill or for the cost of a residential customer who uses a certain amount of water. So to do this, let's start in part A by asking what amount would we have for a water bill for a customer who uses no water. So here, regardless of how much water is being used, we're told that we have a basic service charge of $25 a month, just to be a customer of this group, regardless of how much water is used. So if we are using no water, our cost is $25. Now, in part B of this example, we are asked to find the water bill for a customer who uses 15 CCF or 100 cubic feet. So here, in part B, well, our cost for this customer would be the initial $25 as the basic service charge, regardless of how much water is used. And onto that $25 base charge, we have a charge of $2 per CCF for the first 15 CCF. So for a customer who is using exactly 15 CCF of water, we would have $2 times the 15, so $2 per 100 cubic feet times the 1,500 cubic feet that they used. So here, our cost is $25 plus $30 gives us $55. All right. Now in part C, we're asked to find the water bill for a customer who used 3,000 cubic feet. So let's figure this out. We have our cost would consist of the initial $25 flat service charge, plus for the first 1,500 cubic feet, the cost is $2 per 100 cubic foot. So we have the $2 per 100 cubic foot times the first 15 that we used. And then we were told in the problem statement that the cost is $4 per 100 cubic foot for each 100 cubic feet above the 1,500 cubic feet. So after we exceed that initial 1,500 cubic feet, we have a $4 charge per 100 cubic foot above 15. So the amount that we were using here in total was 30. Now, how far did we go above the initial 15? Well, we would take 30 minus the initial 15 that we've already charged here. So we're left with, for our cost, the initial $25 plus our $2 per 100 cubic foot times the initial 15, which would be 30, which gives us our $55 cost that we had in part B. And then plus $4 per 100 cubic foot times the 15 that we went over the first 1,500 cubic feet. So here we would have 55 plus 60, which leaves us with $115 for the cost. So in part D, let's try to generalize what we've been doing in the previous parts. We are asked to find a function f of x that gives the amount of our water bill if x cubic 100 feet of water is being used. So here, our function that we're finding for cost is piecewise defined. It depends on whether we've used fewer than 1,500 cubic feet or more than 1,500 cubic feet. So initially, we have a $25 base charge. And for the first 1,500 cubic feet, we're charging $2 per 100 cubic feet. So we would take 2 times x, where x is the number of 100 cubic feet of water that's used, provided that the value of x that we're taking is less than or equal to 15. So that is if we're using anywhere from 0 cubic 100 feet of water up through that first 1,500 cubic feet, it's only costing us $2 per the amount that we used, up through 15. Now, if we start to move past 15, our cost changes. So we found the cost for using exactly 1,500 cubic feet in part B was $55. So we have a $55 charge for using 1,500 cubic feet, And for each 100 cubic feet that we use after that initial 15, we're being charged $4. So we would have a $4 charge, and the amount of water used over the initial 1,500 cubic feet would be X minus that initial 15. So in the case that X was 30, we used 1,500 cubic feet past the initial 15. So we would have 15 over there. Or in general, we could take X minus that initial 1,500. And this would be if X is exceeding 15. So we have the following piecewise defined function for our water bill. And in part E, we are asked to sketch the graph of this function. So let's see if we can sketch this here. We're looking at, in the xy plane, points where we're starting from x equals 0. If no water is used, the initial charge to be a customer is $25. And on the interval from x equals 0 to x equals 15, our function was defined as 25 plus 2x. So that is a line of slope 2 with y-intercept at 25. And as we are approaching 15, well, if we're using 1,500 cubic feet, we saw that the cost would be 55. Now, once we moved past 15, our function was defined as 55 plus 4x minus 15. So this now becomes a line of slope 4 as soon as we move past x equals 15. So from here, the slope of our line would increase to be twice as steep, and for all water usage over that initial 1,500 cubic feet. So one application here of piecewise functions, or the graph of a piecewise function, in, say, billing according to electrical or water usage. So in our next part of this section, we'll consider the absolute value of a function. Now, formally, the absolute value of a function, or the absolute value function itself, f of x, defined by the absolute value of x, is actually a piecewise defined function. So the absolute value of x is defined as x as long as the value of x is non-negative. So that is, if you're taking the absolute value of any non-negative number, you get back the exact same number. So geometrically, y equals x, if we're asked to sketch the graph of our absolute value function, well, as long as x is greater than or equal to 0, we have our equation of the function as being y equals x. So we have a line of slope 1 passing through the origin. However, the absolute value function changes definition at 0. If x is negative, then the absolute value of x is taken as negative x. So if x is a negative number, when we take the absolute value, we're taking the negative of that negative number to get its positive value. So geometrically, our graph would be the graph of y equals negative x, which is a line passing through the origin of slope negative 1 for all values of x which are less than 0. So the graph of the absolute value function looks sort of like this V shape. It passes through the origin, it's always positive, and we can think of it as these two line segments of slope positive or negative 1. So as another example, let's consider sketching the graph of the function f of x is the absolute value of 2x minus 4. All right. So let's think about how this function is defined. We know the absolute value function is defined piecewise. So here, this function would be defined either as 2x minus 4 if that value inside the absolute value, 2x minus 4, is non-negative, and it's taken to be the negative of that value, which would be positive 4 minus 2x, if 2x minus 4 were less than 0. Or equivalently, we could write this as 2x minus 4 if we solve this inequality, we have x would be greater than or equal to 2, or 4 minus 2x if x is less than 2. All right. So we're going to change the definition of this function at x equals 2. So here, when x is equal to 2, we would have 4 minus 4, so our function is passing through 2, 0. And for all values of x which are greater than or equal to 2, we have the line 2x minus 4. So it has slope positive 2, y-intercept negative 4, and is passing through this point. So from here, we can draw a line whose slope is positive 2 for all x which is greater than or equal to that value of 2. Now for all values of x which are less than 2, our function is defined as 4 minus 2x, which is the line whose y-intercept is positive 4 and has a slope of negative 2. So our y-intercept, we just said, was positive 4, passing through 0, 4, and the slope of our line is negative 2. So we would have a line that looks something like this. Now, another approach which we could use to sketch the graph of the absolute value of a function would be to ignore the absolute value at first. If we were to just consider the graph of 2x minus 4, that would be a line of slope 2 and y-intercept negative 4. So if we were to move downward 4 units and take the line of slope 2 with that intercept, we would have the following line. Now let's think about what the absolute value does to a quantity. It takes any negative number and it makes it positive. So the part of our graph which was falling below the x-axis, that is where we have negative y values, we're going to reflect that about the x-axis to get this positive segment. And the absolute value takes any value of x that was already positive and leaves it alone. It gives us the exact same value. So that would be an alternative approach to get this same graph. We could first graph the line itself, and for any part where our graph fell below the x-axis, we could reflect it about the x-axis to get the absolute value for that function. Now, in general, we've already been exploring this idea, but we've been considering the graphs of straight line segments so far. And in general, most graphs do not consist of only straight line segments. So the most basic method that we can use for graphing functions is by plotting points. So as some examples of more complicated graphs, let's consider the following. We're asked to sketch the graph of f of x equals the square root of x plus 1. So let's think about where this function is defined even. So in order for this function to be defined as a real number, we know that the expression under the square root has to be non-negative. So that means that the values of x have to be at least -1 for this function to be defined. So let's choose some test values here. If x is -1, then our y value, the value of the function, would be the square root of 0, which is 0. So our graph passes through the point -1, 0. Let's choose another value of x. Say when x is 0, our function would be the square root of 1, which is 1. So we pass through 0, 1. Choosing some other values, let's say when x is 3, we would have the square root of 4, which is 2. So our function passes through the point 3, 2. And lastly, when our x value is, say, 8, f of x would be the square root of 9, or 3. So we would have the point, or the curve passing through 1, 8, and 1, 2, 3. So our curve looks something like this. And we could keep extending this to larger values of x, since our function is defined for all values of x that are greater than or equal to 1. All right. Now, in our next example, we have a similar problem. We're asked to sketch the graph of the piecewise function, which is defined as x squared if x is less than 1, and it's defined as 2 minus 2x if x is greater than or equal to 1. So let's consider the part first where x is less than 1. So we have a function defined as x squared. So let's choose some values of x which are less than 1, maybe starting at 0. Plugging in 0 to our function, we would have 0 squared, which is 0. If I plug in -1, -1 squared is +1. So we're passing through this point. Plugging in -2 for x, -2 squared would be a +4. So we're passing through the point -2, +4. And taking x as -3, -3 squared would be a +9. So we have a point up here. And so our graph looks something like this. And as our x values start to move towards 1, well, the value of 1 squared would be 1. So we start approaching the point 1, 1. And here we would have a hole in the graph of our function at that point. Since our definition of this function changes at x equals 1. Now when x is equal to 1, we change definitions to 2 minus 2x. So if x is equal to 1, that would give us a y value of 0. So we have a closed-in point at 1, 0. And then the graph of this would be a line. We've got the equation 2 minus 2x, which would be a line with y-intercept 2 and slope -2. So from here, we can construct the rest of our line as having a slope of -2, or equivalently by plugging in other points for x. All right. Now in the last part of this section, we'll consider a result that involves the graph of a function known as the vertical line test. So what this theorem says is that no vertical line will intersect the graph of a function, y equals f of x, at more than one point. Therefore, if we have a vertical line which intersects some curve or a graph at more than one point, then that curve or that graph is not the graph of a function. So let's think about it geometrically. Suppose that we have in the xy plane some curve, something that looks like this. Now, for this curve, we're curious whether this is the graph of a function, y equals f of x. So the vertical line test says, well, as long as any vertical line hits this curve in at most one point, then this is the graph of a function. So in the example that I've sketched here, this would be the graph of a function, something of the form y equals f of x. However, let's say that we had something like the following, maybe something that looks like this as our graph, or as our curve. And we can see here that if we were to take vertical lines, well, there are some vertical lines where we're hitting the curve in more than one point. Now, this doesn't mean that every vertical line would have to hit the curve in more than one point. We can see some examples, say out here to the left, where we don't hit the curve at all. But if there is any vertical line which intersects my curve in more than one point, it is not the graph of a function. And the reason for this, or that this theorem works, comes from the definition of a function. So recall that a function is a rule that assigns to each element x in a set A unique element called f of x. So what fails in the vertical line test here is I'm choosing one specific x, and so if I have two separate y values for that one x value, that does not satisfy the definition of a function. I'm getting two different outputs for a single input. So in our last example, I will ask you to determine whether each graph is the graph of a function or not. And I haven't included specific examples, so let's make some up on the spot here. In part A, let's suppose that we have a curve that looks something like this. Sketch this a little more precisely. So in our xy plane, we have some curve that looks like the following. So is this the graph of a function? Well, we ask, does it pass the vertical line test? So as we're taking vertical lines through the plane, we see that each of these vertical lines is intersecting our curve in only one place. So the indicated figure would be the graph of a function. Now in part B, let's say that we had something like this, maybe kind of a Z shape. So we could see here that this fails the vertical line test. There are vertical lines which are intersecting our curve in more than one point. So this is not the graph of a function. All right. So we can define the graph of a function as a set of points such that our y-coordinate is the value of the function at the x-coordinate. And we've seen how to define or how to graph linear functions or piecewise linear functions as well as some piecewise functions that may not consist of just line segments. And at the end of our section, we found that any curve for which we have a vertical line intersecting that curve in more than one point is not the graph of a function.